The next thing we want in this design of the NVIDIA Jetson Orin Nano is the PCB. Where would you get that? So what you do is right click, add layout for any design you get, right? Let's go up a folder and you have this folder called Allegro layout, and that's where they put it. So now we've added a layout to this project. If I want, I could right click, launch PCB viewer to pull up the view in Allegro Presto or whatever software they're used to do the viewer. Okay, so I have opened the board in OrCAD PCB Editor and this OrCAD X Professional Plus. So here, this is the classic viewer, by the way. If you don't have access to this, or think you don't, you do, or should. You go to All in your Cadence folder, OrCAD and Allegro, and PCB Editor. This is the classic interface you want to use if you want to activate SIG-Wave. Presto is a bit simpler interface, but still very capable. So here we go in our quick views, and I'll choose placement top, and this is what it looks like. Magnificent, isn't it? If I pull up the modern 3D view, the 3DX, click on that icon, pulls this up. Look at that. Hold down the shift key and the middle mouse button and it rotates. Would be great to have the 3D models for this thing, but that's fine. We can turn off different models, right? You can also add models, like add your default models in here. Let's say you want to get, see, I don't like the names of these footprints. 0402, that could be a resistor, that could be, you know, we'd have to like go in, hover our mouse over the device and see it's this capacitor. See, I don't like that. I don't like that. I like it if it's consistent with like resistors, capacitors, and everything, but I don't. This capacitor, because then what do you call your resistors? Like, what footprint do you use for your resistors if you call this? I guess. Okay. So what we want to search for is one of our PCIe nets. Oh, that's a device. Okay. Highlight your nets, and you can scroll down and look at the nets from even the 3D view. Okay. And I'll filter for PCIe. Let's reset. Diff pairs. Here we go. And then you have your spacing constraint set that you could sort by, and here's your PCIe Gen 4 signals, right? And look how they're routed. Diff pairs. Okay. For your devices, we could you could do 3D model, suppress boundary shape, or only 3D models. That's a lot better. And notice how these traces are highlighted. There's a little bump in there for to compensate for this curve that came out. The signals traveling at the same speed in each of these, each of the traces. which means this is going to go a bit faster. If this didn't have the bump, this would go further along in the same amount of time than this. This would take a little bit longer. So they introduced the bump as quickly as possible to reduce the chances of common mode noise. Now notice there's a bend up here, and then that means this signal would go a bit further or faster, and then there's a bend this way, so then that needs to go a bit further and slow down. A bend this way and a bend that way. Try to get that as even as possible and within a tolerance. There's a little bit of leeway. How do you find out? You go to the constraints. Okay, so let's remember this signal. PCIe RX1. We're going to close this 3D view, go to our setup constraints. There we go. I don't want count here. Net classes, which would hold diff pairs in there. So PX Gen, here we go. And it holds our diff pairs. And this is the signal you were looking at. So if you want, you could right click and, you know, analyze this thing based on it. But here are the rules that were set. So you have static phase tolerance, where that both signals need to arrive within 1 picosecond of each other. That's extremely tight tolerance. I mean, it's ultra conservative. It's maybe not ultra conservative considering the speed of PCIe, but and the rise times. But at least if you are a little off, even by a little bit, you have a little bit of leeway. So engineers tend to over design and make sure that fits, and then go with that. And then for your electrical rules, let's see what they put for routing. They use the template. Okay. If I want, I could expand all my rows to see what impedances we're working with in the template. 50 ohms with a 2% tolerance. Okay. In the design notes, pretty sure they mentioned that things can vary by 15%, which is pretty standard. A lot of manufacturers can't get lower than 2%. So I'm not sure who they're using, or maybe this is just a common, a common thing they put here. And then the max amount of delay you can be allowed for any of these nets in the min-max propagation delays, right? For your pins that these come out of and whatnot, and your overall signals is these sets of things. So 0.8 nanoseconds, that's 800 picoseconds. Okay. 4 nanoseconds, 4,000 picoseconds. So there's good leeway here. Total etch length, I don't see I don't imagine there would be a total etch length for a board that's this small. Uncoupled length. Yeah, the maximum uncoupled you can for some of these nets is like 3.81 millimeters or whatnot. You want them to have tight coupling most, if not all the time. Okay. Then you have spacing constraints and all that. Sort of view and look at any spacing constraint rules. They go based on default. But you can put in certain things here, like your 90 diff spacing and all that good stuff. And here's your default. Okay. Now, where would you even set these rules? These are your spacing constraints at class, but there's specific values that you put in here. Okay. Okay, for whatever reason that's not expanding, there we go. And then you have to set those spacing rules, which come from the manufacturer, who manufactures the chip, the rise times, all that stuff. So yeah, and it varies for each board. Same net spacing, Well, varies for each component. Same net spacing, we won't worry about that. This is a pretty tight controlled design. Pretty solid, nothing crazy. And that's the overview of the board design. In the next video, we'll go more in depth into the PCIe.